So, welcome to this lecture. Once again, we are going through dimensional analysis in this course on transport phenomena. I had gone through in some detail trying to explain how we can use dimensional analysis to simplify the design of various systems which are used for transferring heat, mass or momentum. Okay. We had done an example of a heat exchanger, if you recall in the lecture before last, okay, where we had the dependent quantity is an average heat flux, and that depends upon the temperature difference as well as a relatively large number of parameters. We had used dimensional analysis to considerably simplify the number of parameters, and we had got dimensionless groups, the dependent dimensionless group, the Nusselt number, as a function of independent dimensionless groups. In this case, there was a ratio of length, a number that we called the Reynolds number, and a number that we called the Prandtl number. Okay. And I said beyond this you cannot do simply based upon dimensional analysis. You have to derive correlations based upon experiments, or as we shall see in this course, actually do calculations which will give you the forms of these dimensionless numbers. We had also looked at transfer from a particle, okay, transfer of mass from a particle due to the concentration difference between the surface and the bulk fluid far from the particle. In this case, mass transfer depends upon diffusion, okay, and we had once again derived a correlation for the dependent dimensionless group that contains the mass flux, the average mass flux per unit surface area, as a function of other dimensionless numbers, the Reynolds number and the Schmidt number in this case. And I had told you that these dimensionless groups for mass and heat transfer are analogous. If you know the dimensionless, the correlation for mass transfer in terms of the dimensionless groups, the Sherwood number, the Reynolds number and the Schmidt number, you can get an equivalent correlation for heat transfer, where the dependent dimensionless group now is the Nusselt number, the dimensionless heat flux, and the independent groups are the Reynolds number and the Prandtl number. How do these things come about? And that is what we are going to study in the present class. Okay. And I also showed you an example of momentum transfer, where we had looked at the power number for the power in an impeller. Of course, momentum transfer is a little different from heat and mass transfer for reasons that I will come to shortly. Okay. But let us first look at what is the meaning of these dimensionless groups. Okay. If you recall, I had told you right in the beginning that there are two mechanisms of transport. Okay. One is convection. The transport of material carried along with the fluid. Okay. The transport of material because the fluid itself is flowing. Okay. So, if you had some kind of a tube, for example, and there was some fluid flow across some cross section, okay, and that fluid had with it a certain concentration of material or a certain temperature, that would be carried along with the fluid because it is moving as a material. Okay. And if the fluid velocity were u, for example, okay, what would be the flux of mass that was carried across the surface? Okay. The flux, as you know, has dimensions of the mass carried per unit area per unit time. Okay. If there were fluid that were carrying the mass along with it, then the flux that is carried would simply be the concentration of mass in the fluid times the velocity of the fluid. Okay. You can see that the concentration has dimensions of mass per length cubed. Okay. The velocity has dimensions of length per unit time. Therefore, if I multiply these two, I get a flux which is the mass per unit area per unit time. Okay. Basically, whatever material volume element was here initially, after a time delta t, it moves to a new location. That distance traveled is u times delta t. Okay. The volume that is transferred is u into the cross sectional area into delta t. Okay. Therefore, the amount transferred per unit area per unit time will just be equal to the concentration times the velocity. Okay. To explain it again, if I had a volume here, okay, which had a some particular thickness, okay, and some cross sectional area A, after time delta t, it has moved to the right. Okay. The amount that has moved to the right, the volume that has moved to the right is going to be equal to UA times delta t. Okay. Therefore, the mass that has moved to the right is going to be this volume times the concentration. Okay. The mass that has moved to the right is going to be this volume times the concentration. Okay. So, mass transfer is equal to the volume into the concentration. Okay. Therefore, the mass transferred per unit area per unit time, okay, you have to divide by the cross sectional area A, divide by time delta t, and you just get u into the concentration. Okay. So, that is the flux, that is the transport per unit area per unit time due to convection. Okay. Similarly, so this is for mass transfer. For heat transfer, the flux would be just the energy per unit volume times the velocity. Okay. Energy per unit volume times the velocity, where E is the thermal energy per unit volume. Okay. It's basically equal to the mass times the specific heat times the temperature divided by volume. So, it is just equal to rho C times the temperature. Okay. Energy per unit volume times the velocity. Okay. That will be the heat flux that is transferred across the surface. Okay. The momentum flux, of course, we will come to a little later. It's slightly different. Okay. We will deal with it a little differently because the momentum itself is a vector. It's not a scalar like concentration or energy. So, we will deal with it a little differently. So, the point I am making is that as the fluid flows, it carries along with it mass, momentum or energy, and the flux is just equal to the fluid velocity times the local concentration. So, the flux of mass, okay, is equal to the mass density. Okay. Flux of mass across a surface is equal to the mass density times the normal velocity. Okay. That is the velocity perpendicular to the surface. Okay. If I had some surface within the fluid and I wanted to find out what is the mass flux across that surface, internal surface within the fluid, and the fluid had some velocity in some direction u, okay, this mass flux of the surface has to be equal to the component of u along this direction. Okay. The normal velocity to the surface times the concentration. Okay. So, normal velocity to the surface times the concentration, which is the mass density of the fluid, okay, the mass per unit volume of the fluid. Okay. Similarly, flux of energy is equal to energy density, okay, that is the energy per unit volume that I had over here, okay, times the normal velocity. Okay. And analogously, you can always write the flux of momentum. Momentum density times the normal velocity. The only thing that you have to watch out for here is that momentum is also a vector. Okay, so that is convection. Okay, the convective transport of material across the surface, just equal to the normal velocity perpendicular to the surface times the density of either mass, momentum, or energy. Okay. What about the transport due to diffusion? Okay. First, let us take mass diffusion. Okay. This is given by Fick's law of diffusion. So, basically what it states is that if I had some surface within a volume of fluid, and I wanted to find out what is the flux across the surface. Okay. Area of cross section is A, length is L. Okay. The flux of mass across the surface, okay, J will be equal to minus the diffusion coefficient times the difference in concentration between these two. Okay, the difference in concentration between these two locations divided by L. Okay. Recall the flux is mass per unit area per unit time. Okay. Is equal to this diffusion coefficient times concentration has dimensions of mass per unit volume divided by L. Okay. And therefore, this diffusion coefficient has dimensions of length square T inverse. Okay. So, let us write it out, okay, in words. Okay. Flux the flux, which is the rate of transport of mass per unit area per unit time, okay, is equal to the diffusion coefficient times, okay, difference in mass, okay, divided by the length. Okay. So, that is the relationship for diffusion of mass. Okay. And you can easily see I have 1 over area and 1 over time here, and on the right side I have 1 over length. Okay. So, inevitably the diffusion coefficient is going to have I should be careful here. Sorry. Mass difference in mass density, okay, difference in the mass density. Concentration is the mass density, mass per unit volume, okay, divided by a length. Okay. So, I have mass per unit area per unit time in the flux, 1 over length square, 1 over time, and mass density is 1 over length cubed, and then there is another length here. Okay. So, therefore, the diffusion coefficient has dimensions of length square T inverse. Okay. So, there is a fundamental diffusion relationship, okay, for mass. Okay. There is an analogous relationship for heat transfer. Okay. There is an analogous relationship for heat transfer, and the way that works is, okay, if I had instead of mass, okay, I had the heat flux, I wanted to know what is the heat flux Q, okay, due to a temperature difference delta T. Okay. Rather than expressing the heat flux in terms of the temperature difference, I could also express the heat flux in terms of the difference in the energy density of the system. Okay. I could also express it in terms of the energy density of the system. Okay. What is the energy density? It is the energy per unit volume, okay, of the system. Okay. Therefore, you know that the energy is equal to, or the difference in energy between two locations will be equal to m Cp times delta T. Okay. Therefore, the energy density, which is the energy per unit volume, okay, delta E, okay, that is an intensive variable, will be equal to the mass density, mass per unit volume times Cp times delta T. Okay. Therefore, I can as well write delta T is equal to the difference in energy density by rho Cp. Okay. The expression for the heat flux Q is equal to minus K delta T by L. Okay. Q is equal to minus K delta T by L. Okay. If I were to write the temperature in terms of the energy density, okay, I will get minus K by rho Cp delta T delta E by L. Okay. So, what this expression is telling me is that the rate of transport of energy, okay, energy per unit time, okay, when I have expressed the temperature difference in terms of the energy density, is equal to a diffusion coefficient times the difference in the energy density per unit length. Okay. Same expression, okay, except that I have expressed it in terms of the instead of using the temperature difference, I have used the difference in the energy density. Okay. Since I have energy on the left side, energy on the right side, this diffusion coefficient has to necessarily have dimensions of length square per time inverse. Okay. So, this is basically a diffusion coefficient for energy, okay, a thermal diffusivity, if you will. Okay. It is often represented by this symbol alpha. Okay. Alpha is equal to K by rho Cp. Okay. This is a diffusion coefficient for thermal energy. It has dimensions of length square per unit time. Okay. You can verify that. Okay. You can quite easily do dimensional analysis and verify that this has dimensions of length square per unit time. Okay. So, this is a thermal diffusion coefficient. Okay. Now, I can do the same thing for momentum as well. Okay. You know that the Newton's law for viscosity can be written as tau is equal to mu delta U by L. Okay. So, I have the same system here. Okay. Rather than a difference in temperature, I have a difference in the velocity. Okay. Rather than a difference in temperature, I have a difference in the velocity. Okay. So, the top surface is moving at a different velocity than the bottom surface. Okay. And because of that, if I plot the velocity across, okay, I will get a velocity difference, okay, across the surface. Okay. This is how the shear stress is written. Okay. Shear stress is the force exerted per unit area. Okay. Force is a rate of change of momentum. Okay. Change in momentum per unit area per unit time. Okay. So, this is equal to per unit area into time. Okay. So, this is effectively a flux of momentum. Okay. The change in momentum of the volume below is because that momentum has been transferred to the volume above, okay, this surface. Okay. And that change in momentum per unit area per unit time is a momentum flux. Okay. The change in momentum per unit area per unit time is a momentum flux. Okay. Okay. So, this momentum flux I have to express it in terms of the difference in the momentum density. Okay. The momentum, as you know, is equal to the mass times the velocity. Okay. Therefore, the momentum density is equal to mass per unit volume into the velocity, which is equal to rho times u. Okay. So, therefore, I should express the difference in velocity in my expression here in terms of the momentum density, okay, in terms of the momentum density, and that is quite easy to do. Okay. So, the difference in velocity delta u is equal to the momentum density, okay, which is rho delta u by rho. Okay. So, therefore, instead of u, I write down the momentum density as rho delta u by rho. Okay. Then my expression becomes mu by rho into delta of the momentum density by L. Okay. For the present, I will assume that the mass density does not change. Okay. Those are called incompressible fluids. In most fluids, so long as the velocity is smaller than the speed of sound, you can assume that it is incompressible without any loss of generality. Okay. So, therefore, when I express it in terms of the momentum density, okay, okay, I will get a constitutive relation of the form tau is equal to mu by rho delta of the momentum density divided by L. Okay. And this once again has to be a diffusion coefficient. It has to have dimensions of length square per time. Okay. This is what is called the kinematic viscosity nu, which is equal to mu by rho. The ratio of the viscosity and the mass density, okay, that is a diffusivity for momentum. Okay. So, I have tried to explain to you how you can express the constitutive relations. Okay. This, for example, is Newton's law. Okay. Okay. So, the Fourier's law of heat conduction okay, can be expressed as J is equal to minus d delta C by L. Okay. Rate of transport of mass per unit area per unit time is equal to a diffusion coefficient times the difference in the mass density divided by the distance. The Fick's law for diffusion can be expressed as Q is equal to minus K delta E by L. Q is energy transported per unit area per unit time. Delta E, E is the energy density. Okay. And similarly, Newton's law for viscosity, my apologies, it should not be K, it should be the diffusivity alpha. Okay. And Newton's law for viscosity can be written as tau is equal to nu delta of the momentum density divided by L. Okay. And expressed this way, all of these d, alpha and nu are all diffusion coefficients. Okay. They have dimensions of length square per unit time. Okay. So, these basically give you the relative rates of transfer of mass, momentum and energy. Okay. Very often these are written in differential form. Okay. So, this kind of a relationship that we have here is valid only when you have a linear gradient across two surfaces in the fluid. Okay. You can also apply this locally at each location within the fluid, in which case you would use the differential form minus d partial c by partial x where x is the direction perpendicular to the surface. Okay, x is the direction perpendicular to the surface across which the transport is taking place. These differential relations are obtained in the limit as L goes to 0. Okay. In the limit as L goes to 0, delta C by L will be dC by dx. Okay. And it is important to note that you have to take the derivative perpendicular to the surface across which transport is taking place. Okay. In this particular case, the x coordinate will be in this direction. Okay. The other point to note, in both Fourier's law and Fick's law, there is a negative sign. That is because mass is transported from higher concentration to lower concentration. Energy is transported from higher temperature to lower temperature, or from higher energy density to lower energy density. Okay. And Newton's law, we will write it here with a positive sign. I will explain a little later how that positive sign comes about. Okay. So, these are the fundamentals of diffusion. Any quantity, rate of transport of that quantity per unit area per unit time, that is the flux of that quantity, is equal to a diffusion coefficient times the difference in the density of that quantity. Okay. Whether it is mass, momentum or energy, the density of that quantity divided by a length perpendicular to the surface. Okay, or the gradient perpendicular to the surface. And written this way, all the diffusion coefficients have dimensions of length square per unit time. Okay. How can we use this to frame our dimensionless groups? I will come to that in the next lecture. Okay. So, we will look at how we can interpret dimensionless groups in terms of ratios of diffusivities and ratios of convection and diffusion. Okay. And that will give you a much better idea of what these dimensionless groups actually mean. Okay. We will start that in the next lecture. Okay. We will see you then.